and welcome to SDC 2021. NVMe is the de facto in storage industry, and NVMe Fabrics is becoming the backbone of disaggregated storage. And hence, the management of NVMe or Fabric resources becomes crucial. This is Rajalaxmi Angadi here to present DEM, that is Distributed Endpoint Manager, that accelerates Redfish Swordfish development for NVMe and NVMe Fabrics. So today we will be going through what DEM is. Since we are talking about resource management, we will do a quick recap of NVMe and NVMe Fabric resources. We will see how do they look like in SNIA Swordfish. We will then dive into DEM to see its architecture and functionality. Then we will see how it complies with SNIA Swordfish through the CTP. And we will also see some CTP test results as well. So there is work happening in SNIA Swordfish and NVM Express with respect to NVMe or Fabrics management. And DEM is tailing along, so things are evolving at all of these places. So what is DEM? So DEM is a distributed endpoint manager. It is an open source strawman for managing NVMe or Fabric resources. Like the name says, it is a distributed endpoint manager. It manages the endpoints and configures NVMe or Fabric subsystems on them. It does it by getting the list of underlying resources, getting the list of Fabric transport that it has, and configuring them to be an over-the-Fabric subsystem. It can also manage hosts by providing them with the log pages so that the hosts know which subsystems are accessible to them. It can also manage changes or updates to the resources via event notifications. And DEM is also complying with NVMe and Swordfish specifications. So looking into these specifications becomes important for us as these are the places where things are getting defined. NVMe specifications specify architecture and methods for NVMe and NVMe or Fabrics functionality, whereas MI spec defines mechanisms for managing NVMe storage devices. And what about DMTF, Redfish, and Swordfish? These are the standards for delivering simple and secure management for large-scale environments, be it big cloud or data centers. It is a very well-defined management interface that is scalable and also has an extensible data model. It is really useful because it uses web standards and it is also open source. And DEM is an attempt towards tying all of these for the management of NVMe or Fabric resources. Today, we do not have a standard way of configuring over the Fabric resources and something that is also complying with SNIA Swordfish. And that is why we have DEM. And when it comes to resource management, we need to understand NVMe and NVMe or Fabric resources. And where in the spec do we have details for the management of these resources? So the diagram here shows two NVM subsystems. Let us call them as underlying subsystems. And the resources here would be the namespaces, the I/O controllers, the ports, the subsystem itself, etc. The diagram on the right shows the layout of the components for the management of these resources via management controller. And NVMe MI spec specifies the architecture and commands for the management of these underlying resources. We can see there is a management controller interface, there is a management endpoint, there is a SM bus interface through which the management commands are communicated. An NVMe or Fabric subsystem, it is an abstraction that is created by using underlying resources. In this simple example, we have carved out the namespaces from each of these underlying subsystems. And there is a Fabric transport configured and there is host access configured on this. NVMe Consortium is working towards closing this gap for the management of NVMe or Fabric resources. And it is doing it through the technical proposal TP6011. And DEM is a strawman prototype for managing NVMe or Fabric's resources. So on the lower end towards the device, we need methods from these specifications to carry out the management functionality. But on the outside, there can be one management tool or a universal management tool that complies with Redfish and Swordfish to manage various resources. Imagine a Redfish or Swordfish compliant tool is sending a management command to manage one of the resources. It will have to percolate down and come down to either one of those NVMe or NVMe-MI methods for it to carry out that functionality. Hence, we need to understand how the resources are laid out or represented in both Redfish and Swordfish and how they map into our NVMe model as well. So Redfish is a standard from DMTF, and it defines protocol schemas, host interfaces, etc. for the management of servers. And SNIA Swordfish extends it for the storage management. My colleague Phil Caton spoke about NVMe or Fabric's resource management in Swordfish, and Rishal have explained us why we need Swordfish and what's happening in Swordfish. But to understand the role of Swordfish in NVMe or Fabric's management, that too with respect to DEM, we need to understand how the resources are mapped or represented in Swordfish world. So we have seen this kind of a mapping diagram in multiple presentations today. This is the mapping diagram that shows the mapping between Swordfish and NVMe device model. And this is for the underlying subsystem. Remember, we saw there were like two underlying subsystems in our previous slides. And moving on to an over the fabric subsystem. So this shows the mapping for NVMe or Fabric subsystem. It shows like the volumes in the Swordfish are mapped to the namespaces in the over the fabric model. And we can see the endpoints are used to represent the fabric transport, which is an exported port there. The connections on the Swordfish side are used to define the host access control on the over the fabric side. We use the term exported here, and that is just to represent that these are NVMe or Fabric subsystem resources, and that is not a standard term. But we need to understand two important things here. One is the mapping between Swordfish and NVMe, and the other thing is we need to understand the properties that are associated with each of these resources. So understanding the mapping will let us know which Swordfish resource we should use in our implementation for a corresponding NVMe or NVMe or Fabric resource. And understanding the properties of each of these resources, that will help us implement the management software in such a way that it will comply with Swordfish spec. So every Swordfish resource will have a list of properties. And to comply with the Swordfish CTP, the resources needs to be defined in a way that is required by the spec and also with the minimum required properties. So later in the presentation, we will see an example of a Swordfish resource for this storage resource of Swordfish. And we will see how it is defined and how it links with some of these other resources. But now let us dive into them. So we have seen NVMe and NVMe or Fabric resources and their mapping in Swordfish. We know that underlying resources are managed with the commands or methods that are specified in the MI spec. But there is a gap for NVMe or Fabric's management, and DEM is focusing on NVMe or Fabric's management. So let us see how it is architected. So DEM is an open source strawman, and it has these three major components. So these major components are DEM, that is a central entity for managing the hosts and the targets. And EM is an endpoint manager that is associated with a target system that communicates with the DEM and configures an NVMe or Fabric subsystem on it. And AC is an auto connect. It talks with the DEM to know which targets are available for it to connect to, and then make the connection to those targets and can access storage. So let us dive into each of these individual components and see what do they look like and what are their functions. So DEM is a central entity. It is a dynamic configuration and management tool for NVMe or Fabric resources. And how it does is it does it by getting the list of underlying resources on each of the target systems by talking to the endpoint manager. It also maintains the database of all the resources and it instructs a configuration for over the fabric subsystem to the endpoint so that NVMe or fabric subsystem is configured there. On the other side, it talks with the hosts or initiators and provide them with discovery log page information so that those hosts will know which subsystems are available for them to connect to. It can also manage event notifications in case of any changes with respect to any resources or the hosts, etc. And it is an interpreter which will talk Swordfish and interpret to NVMe and vice versa. So DEM acts like a pseudo target for the hosts because the host will ask the DEM to provide information about the subsystems. And DEM acts like a host to the endpoint manager or the target systems because it is asking for all the information from there. So DEM is kind of that one central glue which is providing this connection. And to begin with, if the hosts and targets are registered, they will all be getting the messages in sync. But if they are not registered, then they have to proactively connect with them to get to know the information. And DEM can reside on one central management server, or it could be in the cloud. And like I said, it can take Swordfish requests, or it can cater to the command line requests. So EM, it is an endpoint manager, and it resides on a target system. What it does is it collects the list of all the underlying resources it has, like, for example, what subsystems it has, what namespaces are available from those subsystems, what are the fabric transports that are available, and it can communicate that with DEM and get configuration information from DEM so that an NVMe fabric subsystem can be configured. And it can also supply it with the log pages and also, like, communicate with them for any changes with respect to these resources. So if an endpoint manager is registered with the DEM, on the bring up, the DEM will automatically query it for the resources. So if it is not registered, then it has to be manually configured with the DEM. So today we do not have a method for automatically knowing the details of the DEM, like where it resides and everything. So it has to be manually configured. Moving on to auto connect. This resides on the hosts, and the hosts again talk with DEM, and they all collect discovery log page information from DEM so that they will know which subsystems are configured for them, and in turn connect with those subsystems to access the storage. So similarly, if the host auto connect is not registered with the DEM, they will have to proactively ask DEM for the information. And if they are configured, we can have DEM to send the notifications about subsystems that are newly configured and that are allowed for this particular host, or if there are any changes to the resources that are already configured for this host. So basically, all of these three work in sync so that the subsystems are configured and they are accessed by the remote hosts. So now that we have seen these components and what do they do, let us see how they interact. So DEM is a central entity. It takes commands or methods from management client. It could be in the form of HTTP request, be it be Swordfish or Redfish URI or a command CLI. It maintains that resource database. It talks with the endpoint manager and gets the list of underlying resources. And it sends configuration to this endpoint manager so that NVMe or fabric subsystem can be configured. The NVMe or fabric subsystem can be a restricted one, or it could be an unrestricted one. So when unrestricted one, like the name says, it can be accessed by any host. And a restricted one will be restricted to some set of hosts that are defined for it. So once it is configured, it also supplies it with all the log page information. And in this case, DEM is acting like a host, and Endpoint Manager is a target here. And on the other side, it communicates with the DEM Auto Connect, which will collect all the discovery log page information from DEM, and it will know which are the subsystems that are available for it to connect to. And in this case, DEM acts like a target, and DEM Auto Connect will act like a host, and it will know the subsystems that are provisioned for it and then makes a connection to those subsystems. And that is shown by the data path over there. And DEM also maintains the resource tree in a form that is compliant with Swordfish, and it can be validated with Swordfish CTP. So later in the slides, we can see some CTP test results as well. This dotted line between management client and the DEM Auto Connect or endpoint, it shows that the management client can be one generic management client that can send commands to these systems as well. For example, to get health status or to get the list of hardware inventory that these systems have. So moving on to see the DEM functions. These are the main DEM functions, and we will see a quick demo of DEM in action along with these functions as well. So the basic functions are to get the list of underlying resources, like what subsystems are available, what are the namespaces that are available from those subsystems, and also getting the list of fabrics that we can use for exporting these subsystems. And followed by configuring a subsystem that can be accessed remotely, and adding these storage resources like namespaces to this subsystem. Managing the transport configuration involves configuring one of the many available fabric transports to be associated with this subsystem. And host access rights configuration deals with specifying whether subsystem is restricted one or unrestricted one, and which hosts are allowed access to this subsystem. So let us quickly dive into our demo and see how it functions. So I'm logging into the DEM, and let us create a subsystem. For first one, let us create an unrestricted subsystem, and I will call this as NVMe-oF Subsystems. And I will create it on a target system that is, on an endpoint that is residing at this IP address, and it is talking to me over this port. And we can see on this endpoint, we have some fabric from some fabrics available. And we also are seeing some underlying subsystems and their namespaces that are available for us. Let us configure a subsystem with the standard NQN name. And since we are creating this as an unrestricted subsystem, I am clicking this, checking this allow any host, so that any host can access this subsystem. We can see this subsystem is created and it will be allowed by any hosts. And now this is just an empty subsystem. We need to add or attach some storage to this subsystem. Let us attach one or more of the underlying namespaces to this one. So for our simple configuration, I'm just attaching one namespace here. You can see that namespace is attached. Now we have created an NVMe-oF Fabric subsystem, but we have not attached a fabric through which it can be accessed. So let us go ahead and add the port ID. And since on my system, I just have one interface that is talking RDMA protocol, and it has this IP address, I'm just going to use that. And we will use one transport service ID, that's the port that we will be talking through. And we can see that we have configured an NVMe-oF Fabric subsystem with this fabric transport, and we have attached one namespace to it. So let us also create a subsystem that is restricted one, a subsystem that can be restricted to just one or few hosts. So let us call this as subsys test, but it is restricted. And we are going to create it again on the same endpoint. So now let us go ahead and add details to this one. We can see that we have the interface and we have some list of namespaces available for us. We will again use a standard NQN. And this time we are not going to check allow any host box because we want to restrict it. So we can see this subsystem is here, but it is restricted. It is not open to all the hosts. So now again, we have to add some namespaces to it. I will just do this one like the way we did for unrestricted one. We will add some transport details. And now, since we have made this restricted, it will not be open for any hosts. So we need to add some hosts to it. So right now, amongst all the list of hosts that are available, I just have just one host in my demo. So I'm going to add this one to this subsystem. So now we have configured a restricted subsystem, which is allowed only for this host. So this is how DEM works with respect to configuring a subsystem. Moving back to the presentation. So we will quickly see some snapshot of all of these functions. And we have already seen all of these in our demo as well. So this shows the list of how the DEM endpoint lists the resources that it has, like the fabric transport details and the subsystems and namespaces that it has. And for creating an NVMe fabric subsystem, we specify where we want to create, like on which endpoint we want to create the subsystem. We mention the NQN, and we see the subsystem is created. So the subsystem is just like a blank envelope. It does not have the storage resource yet. We need to attach namespaces to this subsystem. So when we want to attach namespaces, we can find that it shows us the list of namespaces that are available, and we can add one or more namespaces to this one. In our demo, we have seen a simple example, but there can be more complex configurations wherein the underlying namespaces that you are showing could be aggregate of one or more namespaces, or it could be like part of the namespaces. But whatever is being shown as an underlying namespace, we can use that to configure our over the fabric subsystem. So we can see that a subsystem is configured, and this one is showing the fabric transport information and how it is configured. And thereby we have created an unrestricted subsystem here. And for this restricted one, all we do is we do not check this allow any box, and we additionally have to configure what hosts we want to give access to. And in this example, we have just given access to one host. And this is our restricted subsystem. So we have seen how the resources are configured with the DEM. We also want to see how these are represented in Swordfish. So the diagram on this slide shows an example of the storage resource for an NVMe fabric subsystem. And this is our NVMe-oF _ subsystem. And we see we have given it an NQN here. And it has resources like volumes, controllers, endpoints, etc. And it is not showing the connections link here because I just cropped it to fit this slide. So it will have more on this resource as well. So for the volume, it is showing the volume resource here, and volume is coming from one of the providing pools, and which is linked with underlying subsystems namespace here. And the endpoint, this represents the fabric transport, and we can see that this endpoint is associated with this subsystem, and it has fabric transport details like the protocol, the IP address, and the transport service ID as well. So there shall be an agent that will interpret Swordfish to NVMe and vice versa. So now that we have seen DEM in action and how resources represented in Swordfish, let us see how DEM complies with Swordfish. But before that, what is CTP? CTP is an open source suite that will help you validate if your resources are compliant with SNIA's storage management specification. And it also helps vendors to validate if their resources are defined in a standard way or not, and also if their resources are having minimum required properties or not. And it can help validate like your products to see if they are conforming with a particular version of management API specification or not, etc. And you can find more details about the CTP on this link. So where in the DEM we have a Swordfish interface. So the blue shaded areas can be places for handling Swordfish interface. We want it towards the management client because we want to access, we want to be able to cater to Swordfish requests. And it could be towards the Endpoint Manager interface as well, because we want to have Endpoint Manager to be able to cater to Swordfish requests. And we, like I said before, there shall be this agent interpreter for Swordfish to NVMe and vice versa. So this slide shows the snippet of a CTP test command. And on the right, it shows like what resource requests the DEM is getting. We can see that DEM is getting requests for so many resources, and it replies them to the CTP. After the tests are done, the CTP results are displayed in a nice web page format. And it looks something like this. And these are the results of CTP that is run against DEM. So DEM is in turn helping validate Swordfish CTP as well, because things are also like, being worked on at the CTP side as well. So we can see if it is green, the resource is passed. And if there is red, it means there is some non-compliance or there is some issue. And we can see a red here because we're still working on complying with CTP completely. So continuing more on the CTP results, CTP can show you like details about resources as well. For example, we can see this namespace resource here, and all you have to do is click on that show results, and we can see the details of this resource. It is showing us the list of all the properties that this NVMe namespace resource has, and it is showing the pass as green for the resource properties. Like I said before, there are some properties that you need to have in your resource, and if they are not, then the CTP will flag them, and then you will know that okay, these are the properties that are defined by the specification to be mandatory, so we need to have them. So all in all, CTP is easy to use, and the test results on the web interface are really helpful to interpret. And it is good when you comply with the Swordfish CTP. That will give you a check mark that, okay, your product is now complying with the Swordfish CTP. That brings us towards the end of this presentation. And to summarize, where does DEM stands right now? So DEM is just a prototype for NVMe Fabric Resource Management. And since there is work happening in NVMe and SNIA Swordfish with respect to NVMe Fabrics Management, DEM currently works with an emulated system for the CTP. And DEM will need to evolve with the base specification when NVMe Fabrics Management commands are added to it. And the interpreter agent also will need to evolve too with a SNIA Swordfish development. And some of the features like the event notifications and managing the hosts and targets are not fully baked in, but the basic functionality works. So we know that SNIA Swordfish has already added NVMe profiles and markups and mapping guides for NVMe, and it is also making progress for NVMe Fabrics. So DEM will try to keep up with all of these and will evolve along with these specifications. The GitHub link for DEM is shown on this slide. There is an extensive wiki. Please feel free to explore, and you are welcome to contribute as well. And this slide has all the useful information about all the various standard bodies and working groups. And you can see and explore these places to see what work is happening into these working groups. And you can join whatever interests you. And that brings me towards the end. And please take a moment to rate this session, because your feedback is really important for us. Thank you.